Hi, folks. This time, as we talk about magnetism, we're going to talk most specifically about Earth's magnetic field. Now, the magnetic field around the Earth is very similar in shape to the magnetic field around a bar magnet. Typically, when we make a magnetic field around a bar magnet in a lab, it's going to look like this because we do it on a sheet of paper and we see it two-dimensionally. But the magnetic field around planet Earth, of course, is three-dimensional. And so it surrounds us, emanating from the magnetic poles and surrounding the Earth very much in the shape of a large bagel or a large donut. So it totally encircles the Earth. If you have ever navigated on a hike through the woods when you're out hunting or exploring, perhaps boating, flying an airplane, things like that, you have used a magnetic compass to help find your way. Before the invention of GPS and more sophisticated navigational methods, this was the way that ships and planes, the only way that they had to navigate from point to point. Now, what causes the Earth's magnetic field? The Earth's magnetic field is caused by the rotation of magnetic metals within the outer core of the Earth. The Earth has many layers. When it was a young planet, it was made of many components, and they have sort of parfaited out. The heavy, dense things, the iron and nickel, has sunk to the center, and the lighter weight rocks are on the outside edge. Through time, the Earth has cooled. The original heat, the original kinetic energy from the creation of the Earth, from the rocks colliding with each other, combined with heat produced by nuclear reactions, as those rocks have decayed via nuclear decay, have kept that Earth, our Earth, warm. Now, the actual center of the Earth is a ball of solid iron. And how do we know this? We know this by analyzing earthquake waves. Beyond the solid iron and nickel core, there is a outer core that is liquid, fluid, liquid iron and nickel. Now, that fluid and liquid iron and nickel contains convection currents. If you remember convection currents, things that are hot have a tendency to be less dense and rise. They cool, they become more dense and sink. And that hot core, they rise, they get away from that hot core, cool and sink. Well, these materials are magnetic. They also, because they are metals, they can conduct an electric charge, and this rotating, moving metal produces a small current within, electrical current within the Earth's interior. And this constant rotating motion within the center of the Earth produces this magnetic field around our planet that comes out and emanates outward from that planet in all directions. Couple things that are really fascinating about the Earth's magnetic field. One is that it is not, the magnetic north is not at the same location as the geographic North Pole. If you remember from geography class, there is true north. The true north is straight at the top of the ball. True geographic south is at the bottom of the ball. And those are 0 degrees latitude up north and 0 degrees latitude south. But because of the fact that this magnetic field is produced by rotating fluids inside of this ball, those rotating fluids can move and oscillate and change. And so the magnetic north is a little bit cattywampus. It's a little bit off from true north. Matter of fact, it is a few degrees off from that geographic true north. The difference between magnetic north and true geographic north has a name, and the name is called magnetic declination. Now, those of us who live in the Midwestern part of the United States, this is not a big deal if you are ever trying to navigate with a magnetic compass. And the reason is because we live in a place where both of them are kind of below both magnetic north and true north. So if you go out with your magnetic compass, both of them are going to point towards the top of the ball. And so we're going to manage quite well out in the woods. The challenge occurs if you have a tendency to be navigating further west or further east. The difference between the top of the ball and magnetic north can be a lot. And I like this picture down here because for the continental United States, it gives us a nice illustration. If you happen to be going for a hike in Maine, the difference between true north and magnetic north can be 20 degrees off. And we all know that you can be out in the wilds of the mountains of Maine and you cannot get a GPS signal or any phone signal, so you're going to have to use a magnetic compass to navigate. And without this piece of knowledge, you can be quite a ways off. Same thing in the wilds of Washington State, Oregon State, Montana. Hunting out there, you can be quite a ways off in your navigation. So those of us who hang out in the Midwest, those of us in western Wisconsin specifically, we're right about the line of zero declination, meaning there is no difference between the two. One of the other things I wanted to mention, and let's go back here for a second, that I think is pretty fascinating. If you are trying to navigate with a magnetic compass, the north-seeking pole is going to point towards the top of the ball. Now, what we referred to as the north-seeking pole of your compass is going to point here. So we know that unlike poles are going to attract. So what that means is that inside of the Earth, there is actually, at the top end of the ball, there is a south pole. Yeah, so what we call the North Pole, because the north-seeking pole of the compass points that way, actually inside the Earth contains a south magnetic pole. I hope I didn't mess your brains up too much there. It's kind of a wacky concept. Here's another weird thing about the Earth's magnetic field. It changes, and it changes through time, and it changes quickly. There's not a lot of things in geology that change this quickly. The motion changes because the metals inside that outer core are rotating. These eddy currents of rotating metal due to convection are constantly in flux and moving. And these things change in a human lifespan. That these have been measured. So those of you who are in your 20s, maybe 20 years ago, it was at closer to 80 degrees north latitude as opposed to closer to the year 2020, where magnetic north is a lot closer to 90 degrees north latitude. People who are closer to 40 years old, it's a little further down, and about 100 years ago, the magnetic north was closer to 70 degrees north latitude. So it has changed, and these markings have been noted by navigators and cartographers for a long time. Another wacky thing about the Earth's magnetic field is it not only moves around, it flips, completely flips over. The last recorded flip occurred approximately 780,000 years ago. This was a shock when it was discovered back in the late 1950s, early 1960s. There were boats that were traveling across the Atlantic Ocean, and they were taking core samples. What that meant is that periodically they would dig down into the ocean floor and they took some sediments. When they brought them up, took them back to the lab, one of the things they looked at was the magnetic orientation of the rocks that they brought up. In the middle of the Atlantic Ocean, there's a thing called the Mid-Atlantic Ridge, and this is a group of volcanoes. And what the volcanoes spew up are lava, and this is liquid rock. And the liquid rock, when it comes up, the rocks are going to freeze in the magnetized bits, the iron, cobalt, and nickel bits, are going to freeze in the orientation of where magnetic north is at that point in time. And what they found is that at the current point in time, magnetic north is that way. Many years back, about 780,000 years ago, magnetic north was pointed towards the south. You get further away from the Mid-Atlantic Ridge, and magnetic north was back up north again. You get further away and magnetic north was pointed south again. And that's what this zebra stripe picture is supposed to illustrate. The magnetic field has totally flip-flopped over many, many, many times in history, the history of our planet. The next flip-flop is predicted by geologists in about 10,000 years. What is that going to mean to navigation, to animals, to animals that are going to be migrating from here or there? Most of the biologists that I have ever read about or talked to say there's not typically a major die-off of species around these magnetic flip-flops. So species have been able to adapt, which is pretty cool. But it is another interesting factor because our magnetic field is a dynamic and changing thing. Now, the Earth's magnetic field extends out into space. Like I mentioned, it's like a big bagel that totally surrounds the Earth. And there's a thing called solar wind. Our sun is constantly throwing out charged particles, protons, neutrons, and electrons that are coming from the sun. Along with light, it throws out pieces of itself, little microscopic pieces of itself. As these pieces fly by the Earth, some of these charged particles, specifically like protons and electrons, are going to get trapped in the Earth's magnetic field. And these things are going to ride our magnetic field sort of like electricity in a wire. And they're going to ride these magnetic field lines, and they're going to ride the field lines where the field lines cut through the Earth's atmosphere. When these field lines cut through the Earth's atmosphere, they excite or energize the air. And when they excite or energize the air, they make it light up. And when it lights up, very much like when electricity goes into a fluorescent light bulb, then you see the air glow. And that is what causes the northern lights or the aurora borealis. The northern lights or aurora borealis are going to be the strongest at the north magnetic pole and, of course, the south magnetic pole. Other planets have auroras if they have an atmosphere and a magnetic field. We've seen these specifically. Jupiter, Saturn, Uranus, Neptune all have very, very beautiful auroras, as well as planet Earth, but these are the ones closest to home. The Earth's magnetic field is also fabulous because it helps protect us from having our atmosphere stripped away. The sun periodically not only has the solar wind that it aims at us continuously, periodically it has things which are called coronal mass ejections. These are huge events. They're like a solar storm, vast quantities. These are bits of high energy particles that are aimed out into space. And if one of these happens to be aimed directly at the Earth, it could strip or scour our atmosphere away. Well, these particles get into our magnetic field. Most of the particles are going to be deviated around the Earth by our Earth's magnetic field. A few will penetrate and will create some spectacular auroras, but most of them are going to go around and it will protect our atmosphere. By contrast, our dear friend Mars is about 1/3 the size of the Earth. It has a very weak magnetic field. It has no liquid core, and that's one of the reasons that it has a very weak magnetic field. And because of that, through time, Mars's atmosphere, to a great extent, has been stripped away by the solar wind. And so there's just not much of an atmosphere at all on Mars, if you happen to plan on colonizing Mars someday. All right, have a grand day, and we'll talk to you later.